Okay, what I want to do in this video is just play around a bit with logistic regression and provide some visualization of what this looks like. What I don't want to do is try to give some kind of mathematical, rigorous explanations behind logistic regression. Or saying it in other words, what I hope to achieve is to show that the way how logistic regression typically is presented, that this indeed works. What I don't want to do is say, okay, this is an explanation why this is the only way how it has to be done in this way. Okay, so I'm going to talk about logistic regression, and in general this then extends further towards other general linear models, to this idea of using link functions. Okay, let's jump in, and we are going to start off with just regular linear regression, just to remind ourselves a little bit of some concepts, some terms. And I'm just going to copy in some data here. So what we have here is a data frame, weight, which is a metric variable, gram of body fat, another metric variable. This is inspired by data used in StatQuest, where just Summer talks about the weight of mice and then whether these mice are obese or not. So our third variable is the obesity status. And here you can see this one is not a metric variable, but this is just 0 or 1s, not obese or obese. Okay, so we have selected just 10 to 20 as weights, and then here we will plot it in a minute. You see that these values increase. They don't increase strictly monotonously, but you see that there's an increase in gram of body fat with weight, as you would expect for real data. Okay, so let's get this data frame in, and then, as I said, let's just make a little plot of that. Weight versus grams of body fat on the y-axis, and I'll change the axis limits a bit. And label it okay, so looks like this. And now the goal of simple linear regression, again where we have just two metric variables on each of the axes, is to find a straight line that minimizes the distance to the points. The reason why I've plotted it in this weird way that we have this huge white space is that we then can interpret those two parameters. So we are going to have an intercept parameter and a slope parameter, and the intercept is obviously where we're cutting the y-axis, which is typically plotted at an x value of 0, and so just that we can see that where this intercept would occur in all this white space. Okay, so what we need now, or what we do now, is essentially we just guess for a potential line that could lie in here. As I said, we need parameters of intercept and slope, and I'm just going to say intercept a0, let's put it just to -1, and our slope a1, let's put it to 3, and then we do a simple AB line, which is called here A, which was our a0, and then the slope is called here B, which I called above A1. Okay, and we just put that in, and I should also initialize this variable first, of course. And now you see this one is our line, and yeah, that's not a particularly good fit. But well, that was just some more or less random initial guess. What we're going to do is now trying to find better values. And I'm going to say, well, this intercept maybe is not that terrible. If we find a slope that is better, then we might get closer to these points. I mean, that's the idea, right? Getting closer to those points. Let's lower our slope and say the slope is 1 and redraw the plot. And we see, okay, yeah, that slope that seems much more reasonable, but we want this line to be lower, so we also lower our intercept a bit. Again, all of this is just playing around a bit, not very systematic. Let's do the complete plot again. And we see, okay, yeah, this is much better now. Probably still not a perfect line, but we're definitely getting there. What does this mean, getting there? I'm pretty sure that, if you're interested in this kind of content, then you know about least squares, which is what people typically use. So they say we take the distance of every point from our estimated line, and then we square it up. And for each of these points, we add it up. And then we want the line where this value is minimal. So minimizing the sum of squares, or doing least squares regression. Now, this is typically the case, or often the case in statistics teaching, that you kind of get these recipes and you follow these recipes and then you get the answer. I mean, similar if you learn probably about a t-test or kind of other things in statistics. Sometimes I think it's nicer to actually think about what is behind this and what are the assumptions. And in this case of linear regression, the assumption actually is that these points are distributed with a normal distribution from the line. So the line would specify the mean value of this normal distribution. And then you ask, okay, how likely is it if we have this normal distribution to end up with a point at this given distance? And essentially what you then say is I calculate the likelihood, the probability of the data point given the parameter, which in this case would be the mean given by the line. And then you multiply all of those likelihoods, and you want in this case the maximum likelihood. So the line where when you multiply all of these individual likelihoods, where you maximize it. Okay, so this was the case of simple linear regression, metric variable on the x-axis and on the y-axis. And now we go to this other variable that we have here, the obesity status. And we're again just going to start off with a plot. So we say plot data frame white, again explanatory variable, and obese as our response variable. Yeah, we can again say YLab obesity status, and I'll just make the labeling for the y-axis a bit different. The reason for changing this labeling is just because I haven't told R that this one is actually a factor rather than a numerical variable. So I don't want to have any numbers between the 0 and 1 here, but only saying, okay, all the values it can take is 0, 1. So we can also put a nicer X label, of course. Okay, so we have, again, a metric variable weight as before, and then our y variable is not metric anymore, but is binary, so we can only get these states 0 or 1. And now, of course, you see trying to, again, fit a line as we did before in the simple linear regression, this doesn't make sense anymore. You would go, you can imagine going to very low weights, and especially you can imagine going to very high weights, and then this line would extend way beyond the allowed values. It would extend probably to negative values, and it would extend to values way above 1, which doesn't really make sense for this example. So we need some kind of different way of fitting something in here. Okay, as I said, what we want to do is we want to just play around a bit. I'm going to set up a new plot for this. I'm just going to copy this over, and if you want, you can look at it later in more detail or pause the video and look at it, but there's nothing too special about this. So what I did here is essentially just repeat this plot as the upper plot with the binary 0, 1 here. And then we have our lower plot. And what I did here, I just put a y-axis, which is, again, like a metric y-axis, which is not 0 to 1, but essentially which extends from -∞ to infinity. I've chosen limited it to a certain range here because I've already played a bit with this data before. And this is kind of a sensible range where we want to look, but there is nothing very particular about these values. And what we're going to do now, we're just going to this lower plot, to this completely separate space from our data, and we're going to put a straight line in here. And this is weird, and it is maybe, yeah, I also find that weird to just say, okay, now we forget about our data and just go to somewhere completely else. But if you can make this leap with me, then you have gotten a good step closer to getting this situation or understanding a bit more how this logistic regression works. Okay, so again, the x values are matched to the plotted path, and this one is more or less just selected by me because I know this is kind of where we want to look at, but there's nothing specific about this. This is just this axis goes from -∞ to infinity. Okay, as I said, we want to put a line in here, guess a line. So I say again, we put a intercept, and I'll just put it at -5, and we'll take the slope, and I'll just put it at 1. And then in this case, I call this the predicted value by the line, which is intercept plus slope times our explanatory variable. And then we can put this into our lower plot as a line. Here I'm just making sure that it's actually getting put into the lower plot. To handle this properly, I'll also repeat this plot. This is also not hugely important here. And then we can just say, all right, let's take those values and plot it. Okay, and you see we have some kind of line in a space unrelated to our data. That's the first step of our logistic regression. Okay, and now we somehow want to go from this space down here to actually our data, somehow transform this line in a way that it makes sense on this space that only covers 0 to 1. So going from a space that's -∞ to infinity to a space that's only 0, 1. And then we'll here assess how good that fit is, go back to our other space, change the line a bit, go back in here, ask, is this a better or a worse fit, and so on. So we need, in the first step, some kind of transformation that brings us from a scale of -∞ to infinity to a scale 0 to 1. And what people use here is the so-called logistic function, which is also why this is called logistic regression. I'm going to type out the function, and I'm going to call it theta, what comes out of it, and it is 1 divided by 1 plus e to the negative of our y value, which I called y pred. So again, going from this scale here now into this plot up here, I'm calling that theta, and yeah, now we'll just plot that as a line in the upper plot. Again, I'm just going to copy that over. And we'll put it in here as a blue line, and calling that theta now. So the black points are our obesity status. Sorry, and the blue one is now the theta, the transformation of this line into this space. What we see is that's not great, obviously. So now we can talk bit more about, okay, how do we, or maybe let's first just go and say, okay, well, how do these functions look like when we transform them? But we can already say this is probably not quite what we want, because this line seems to fit well those upper points. But for here, we would like something where the blue line is obviously closer to this point, so where it's low here. Let's just keep playing around a bit, and let's try, somehow if this slope here is less steep, then maybe these values up here are not all that high, but we can get them a bit lower here. So we'll reduce the steepness of this slope a bit, and let's go from 1 to 0.1, and then let's redo all of this plot. And what we see is, okay, I have overdone it a bit, so now we fit very well those points down here. Just the ones up here, they don't really match our new line very well now. Let's maybe try to go somewhere a bit more in between those two, slope of 0.3. Okay, and now we see what this can look like. You see this is not really a line, but some kind of other curve. And now we're getting to close to what we want. This one is a function now that can only extend between 0 and 1. And what we would like, what we would imagine what should come out of this is kind of a line that goes like this. So down here, and then at those points in the middle where it's less decided, it somehow goes up, and then up here, it's close to these points. So now that we have found a way of, in one space, we can change our parameters a bit and try to find good ones, and then we have found a transformation to go into the space that we actually want. Now we need to ask, okay, how do we assess this one? Would we still use this normal distribution? And again, that wouldn't be a great idea to use a normal distribution here. What kind of data could that be if we have a binary outcome? This kind of reminds us of coin flipping and of the Bernoulli distribution, where you have an outcome of 0 or 1, of head or tail. So what people say, and this is why I call this theta, is you can say, okay, this line gives you the coin bias, and then you ask, given this coin bias, how likely is it that I get, let's call this one here the heads, and this one here the non-heads or the tails, and use this to maximize, again, your expectation. So statisticians are not that super creative, so instead of thinking about something else where you have two outcomes, they still stick with the coin and say, yeah, but there are not only coins that give you 50-50 heads or tails, but you have these biased coins that come up, for example, 90% heads, somewhere up here, or that come up only 10% heads, or anything in between. So this is the way how we're going to assess the fit of our curve to our data, by saying this parameter theta is our coin bias, and asking how likely is it to get this outcome. So we could say, obviously, if we would have a very low coin bias here and we observe a not head, then this would give us a high probability. And on the other hand side, if we would have a very high probability of getting heads, but we observe non-head, then this would not be good. This gives us a low likelihood. And then similar as before with the normal distribution, we can consider all of the points and ask what is our overall likelihood for all of these data. So let's actually go and do this as an evaluation of this curve that we fit in here. So what we say is a likelihood from a Bernoulli distribution. Now the thing is, in base R, there actually is no function for a Bernoulli distribution, but you use the binomial distribution because the Bernoulli distribution is kind of a special case of the binomial distribution where you just do a single flip. So we use the binom for our Bernoulli distribution, and then we say for our outcomes, these are now the obesity status, right? So outcome equals df obese. And as I said, it's a Bernoulli distribution, so a single flip. So we put size to 1, and then we have to put the probability, and this one would be our line, our theta. So now, okay, this is plotted here as a line, but what we actually did calculating this theta is we say for each point where we have a weight, we calculate a theta parameter. So this is actually, not something continuous, but this is a vector. Oopsie. This is a vector which has one of these theta values, one of these coin biases for each of our weights. So you can see vector of size 12. So now if we can do this deep binom here, and we will get a probability for each point given the corresponding coin bias that the line tells us. So what we could do now, or actually let's execute this quickly, and you see these ones are our probabilities for each of these points. What we could do now, we could just say, okay, to have the overall bias for all the points, we obviously have to make the product of these probabilities. So we just put in prod, and we get this value here. So usually this is not what people do, because if you have very low values in here and you multiply low values a lot of times, then you can get very low and you can get towards numerical instabilities in your calculations. So what people prefer to do here is to log transform this and then to take the sum of the logs, because if you're in the log space, you can sum rather than taking a product. And then this one would be called log likelihood instead of when we did the product, which was the likelihood. So this one is essentially just for the way it's computed. You could also do the product as long as you don't run into numerical problems. But because the likelihood is easier to interpret, because that's essentially on a probability space, on a 0 to 1 space, I'll just retransform it by saying, okay, now I take e to the log likelihood. And what we could do now is we could just put it in our upper plot. So I'll just write it somewhere in our plot at a point where it fits. 14.5. And that's our likelihood. Okay, yeah, has a bit many positions after the comma, but that's fine. So we see at this given line, this one is our likelihood, and now we can keep playing around, changing the parameters down here, doing another transformation, and asking, do we get closer to these points? As I said, our optimal line probably would look like something like this, where it starts off very low and then rises and then is up here. So what we could imagine is that we need to increase this slope here a bit, so that also the steepness up here increases. Let's do that. Let's go to a higher slope. Rerun the code. Again, we just keep playing. We see, okay, now we are not very good at these lower points, but maybe if we shift this line down a bit more, then we could also get covering these lower points a bit more. So we could say go to -8 as an intercept. Okay, that looks better. And we see our likelihood now is 0.006. We could probably go even higher on the slope. Okay, that means we now maybe want to compensate this by shifting this down again a bit. And if we shift it down, then maybe our curve here gets shifted a bit right there. There's nothing, you don't need to understand, the reasoning behind this parameter play. Just imagine it as, playing around with the parameters. But I'll put this to -12 now. Okay, that looks pretty good. Make it again a bit higher here. You see that we have now gotten to a value of 0.0012 essentially. Okay, and now we have a curve that looks like this. The likelihood still is in kind of a similar range, and this is more or less what I was hoping for, how this line should look like. So we cover these lower points well with the low values in our curve. These ones we cover well, and here the data are kind of, undecided, so it's not really clear at this rate what the obesity status should be, and that's also reflected by our curve. So that seems pretty good. Essentially, this is what I wanted to tell you in this video. So we open up this space, which at first seems completely unrelated. We do what we know from our simple linear regression. So we change the slope and the intercept, have a line in here. Typically people are not showing this alternative space here. And then we have this transformation function that brings us from a space that has minus infinity to infinity and brings us to the 0, 1 space. Okay, I didn't really tell you much about this logistic function. We can think about it. So we have 1 divided by 1 plus e to the minus what the y value was here. Let's imagine we put a minus infinity here into this y value. Then we get a very high value here, right? Which means our denominator gets very high. 1 divided by something very high means it brings us close to 0. And on the other hand side, if we say, okay, we put a very high value in here, e to the minus something very high is close to 0. So we have essentially 1 divided by 1, which is 1. So our upper bound is 1. And what would happen if we put in 0, for example, here, then for the y pred, then we would have e to the 0 is 1. So we have 1 divided by 1 plus 1, so 1/2, which means at a value of 0 for y pred, we should be at 1/2. And if we look it up, so here's our y pred, which is 0 approximately here, and then we go up, and okay, this is pretty close to 1/2. So this is what I wanted to talk about in terms of playing around. Now, if you want, we can say, well, if we don't want to do this manually playing around, we could do it in a bit more systematic way and actually let R do that optimization. And for this, I'm just going to copy over a function. Again, you can either pause the video or you can look at it later if you want. I'm calling this function parentplay, and essentially it does what we just did above. So the function takes in the data, which was our data frame, and p, which is parameters, and then in here I just split up these parameters into our intercept and into our slope here in this transform, in this non-data space, in this linear space. I calculate the line, I calculate the theta, so essentially meaning doing this transformation, and then I calculate again the log likelihood. In this case, it's a negative log likelihood, so we have this minus here, which is then returned from this function. The reason for the negative log likelihood is now because we're going to use this function in a optimization algorithm, and optimization algorithms typically are minimization algorithms. So if we want to maximize the likelihood, that means we want to maximize the log likelihood. So if we want to find something to minimize, then we just take the negative log likelihood. So this is also something where there is no very fancy reason for that, but just kind of the way this is typically done. Okay, so we can define our function, and then we do exactly what I said we would do. We put it in an optimization algorithm. One that I frequently use is NLM, nonlinear minimization, but there are other ones. And again, if this is something that's completely unfamiliar to you, that's not all that important. I just want to show that this can also be done in an automated way. So we have an f argument, which would be the function, which is the one that we just defined, our parameter play. Then we put in, so the goal of this function is to optimize our parameters to get the best fit, so to get the minimization of this log likelihood, of the negative log likelihood. But what this function wants, it wants us to give some initial guess of what these parameters could be. Again, the parameters that then end up being the intercept and the slope. And what I put in here is just the values where we also started off our manual optimization, which was -5 and 1. But you could put a lot of different choices in here as starting values. And then we give our data, because they have to go then here into this function, right? And that was our data frame df. And what we get out of this, I'll just call NLM out. Yeah, we get some warning message. We'll just ignore that. And then we say, okay, which estimate did we get from you? NLM out estimate, so meaning the estimate for our parameters, for our optimized parameters. And we see -10 and around 0.7, which was not too far on. Where did we end up here? We were at -12.8, so it's not quite the same, but kind of in a similar ballpark. We can also ask, okay, what is your negative log likelihood in the best possible case that you found? So we can say NLM out minimum. And okay, negative log likelihood is not that helpful for us, so I'll call this neg log likelihood. But to be able to interpret it better, I'll just say put that e to the power, and in this case I first put it back into a log likelihood and then into a likelihood. And what we get is 0.012, so actually not so far away from what we got by our manual plane. So this now just shows, okay, we can also automate this up. We don't need to play around with the parameters ourselves, but we can ask R to do that, R to use an optimization function. Still, typically this is not what people would do. As I said, this logistic regression extends further to this general idea of general linear models. And general linear models, you can also use it for just your normal linear regression. And you can use it for other cases where you not have this situation that you're in a space of -infinity to infinity, so where this simple linear regression doesn't work, but where you need to change something and where you need to change it in the same concept that we described here, that you first optimize in some different space, then you transform, which is called the link function. So you link from a space where you can have just a simple line to however that you to the space where your data are in. And so you have this suite of general linear models in R, of which the logistic regression would be one. So if we want to code that up, we would say GLM. We need to give it a function, which is obese is a function of weight in our case. We need to tell it from which data to take that, which is the data frame. And then the important part of telling it, okay, it's a logistic regression in this case. So our output variable is here binary 0 or 1. We have to say family equals binomial. And again, I don't like too much that this is called binomial. I think calling it Bernoulli would be better, but similar as before, Bernoulli is a special case of binomial. So this is the correct family that we want to use in this case. And what this will output is just a linear model object. We'll just call that logreg for logistic regression. Yeah, this is not correct. And what we can do now is just get a summary of this regression object. And we are not going to look at all of this, but we can look at the estimates, so the estimate of the intercept and the weight. And we see that this is essentially the same as when we did it via this optimization function, and similar to what we got when we played around with it manually. So now you see again these coefficients that you get as an output from a general linear model are actually in this space here, in this space where you can have a straight line, rather than in the space of your data that you're actually interested in, which means this stuff is very difficult to interpret. It usually doesn't help you that much if you want to interpret it. So one thing that we can do now with our model is we can try to predict new values. So let's say we have two new mice, let's say one here at 13, the other one here at 17, and we want to predict, are these mice going to be obese or not? So what we can do here, since we have our R model object, we can just say predict, and then we put in that object, which we called logreg. The new data we have to give in a similar form as our original data, so we have to give it as a data frame, and we'll have to call this variable again weight. We are not going to have to give all of the other stuff that was in this data frame, and so we said we wanted to predict one mouse that's 13 and one that's 17. Yeah, so we could put this in like this, or we can say call this one new data as an argument, and then let's just see what we get out here. And you see we get these two values, and so it's again the case that these values are on this case where we have the line rather than up here in the space of our data. So if we check, we have about -1 here for the mouse that was 13. So if we go here, 13, yep, that's about -1. And the other one, we set 17 as an input, so 1.75. So let's see, 17, yeah, that's probably also right, about 1.75. So again, this is something that's, again, not super helpful for interpretation. In this case, however, there's a way of getting something that's more interpretable. What we do is in the command above, we just type equals response. And now we get values of 0.26 and 0.85. And now if you go here, you see that you're actually in the upper plot. So 13, we got a value of 0.26. And for 17, we got a value of 0.85. So these ones are now our theta values. These ones are our coin biases. And so yeah, with this, I hope that this has been helpful in getting a bit of an intuition or a bit of this ability to visualize what this actually looks like doing this logistic regression, and how this concept extends then also to other cases where you use general linear models and where you use this link function that we used here to map from this space where you can have a line to the space where your data are actually in.